Ria?
So
Andy? Okay, yeah.
hey guys. Welcome to the third installation of our speaker series, featuring guest speaker Gary Bradski. So before we start, we're just gonna go into some norms. If you go to the next slide, please. Yeah, so the norms are pretty basic. Essentially, just if you can, please turn your cameras on. It kind of increases engagement, and it's really nice to be able to see everyone. And also, this kind of depends on Mr. Bradski's preferences, but if possible, please keep your microphones off to avoid distracting anyone, and then also like ask questions in chat or after the presentation, and be sure to actively participate.
Well, I might stop at various points, but
Right.
along the way.
Yeah. And then also just a quick announcement, in exactly a week on November 28th, we're also going to be hosting an alumni panel from 5 to 6 p.m. featuring Derek Cho and like several other people, a total of 5 alumni, and they're all class of either 23 or 22 and 24. And they're going to pretty prestigious engineering universities. So if you guys are at all interested in that, they'll answer questions regarding their college life, STEM. You can ask them about the coronavirus, and especially if you're a senior, you can ask them about their experiences applying to top some colleges. So if you guys are interested in that, we have a link right there, and I believe Ria or someone else is going to send the link in chat right now. And be sure to sign up. Yeah.
Yeah, so Andy, why don't you go ahead and send that link? But we'll send out more communication to all of you about this when we wrap up and send you guys like a post speaker email. But that's all for next week. So moving on, we just want to quickly introduce who we are, since I know a lot of you are not part of the MSET Robotics Club. So MSET is Saratoga High School's essentially robotics and engineering club. We have over 100 students. We also have a lot of parents and mentors who are really passionate about STEM and about engineering and about coming together to create these incredible robots and compete in the first competition. And this club, we have 4 teams. We have 1 FRC team, which you can see in the picture here. We have 3 FTC teams. And so the team that's actually hosting this event today is FTC team 6165. We are the MSET Cuttlefish. And Ayush, I believe you'll explain what this is.
Yeah, so last year's Autonomous had us use computer vision to identify differently colored stones. They were called the sky stones in this event. And using a program called OpenCV, we basically detected at what location the sky stone was and how then to determine which path our robot should take to collect the stones and place them on a stack.
And just to emphasize, this is all completely autonomous. So there's no one controlling this robot right now.
Yeah, and so we use
It looks like Ayush might have frozen, but
basically find where the object was and then go on from there.
Ayush, do you want to go ahead and repeat that? I think your camera froze for a second.
Yeah, sorry, my bad. So we used OpenCV over here for object detection, which is basically differentiating the objects, robot localization to tell where we were on the field, and image detection to basically find out which stones were the sky stones.
And for today's session, let me invite my dear friend and distinguished speaker, Gary Bradski. Now, Gary's name is synonymous with computer vision and machine learning. One of his known innovation or well-known innovations is OpenCV. This is what he created a while ago. This is a computer vision library that's used by millions of people and hundreds of thousands of applications worldwide. Gary has some amazing content and insights to share with us all today. I hope you will all enjoy it. With that, let me invite Gary.
Okay, thanks. I'm going to attempt to share my screen. Okay, hopefully you're seeing PowerPoint.
Yes, that's perfect.
Okay, so I'm putting it into display mode, and hopefully you're still seeing it. Okay, so I'm gonna, I'm gonna ramble on about OpenCV and cover some uses in robotics and many other things. I'm going to end with a little discussion, if I have time, for robots in the mine. I should, in fact, keep a little track of how I'm doing. Of course, my phone just ran out of power, so I don't know what I'm doing. We might be here till midnight. Okay, so I'm going to get started. Oh God, it's okay. Yeah, I'll just go on. I've got some intro, but I was at UC Berkeley and then spent some years working. Oh, God, this thing is not okay. Now it's under my mouse control. So I ended up doing a PhD in cognitive and neural systems. You can kind of think of that as neural networks and the study of the brain. And I went on and did many things. I did stuff in finance, but then I came back to research. And that's where I started OpenCV. And then I got on the DARPA Grand Challenge, where I led the vision team for Stanley that started the autonomous driving. We won the $2 million prize for the DARPA Grand Challenge in 2005, the race across the desert, and that's that car became Waymo. I was also visiting faculty for years at Stanford University. It went on to concentrate on startups. So I did this video surf that sold to Microsoft. There was industrial perception that sold to Google, and I was the one who set up Magic Leap in the Valley, and then we got into a lawsuit. So you can read all about it. Then I founded Array, which sold to Matterport. I have a good track record of, like, my companies don't last very long. But anyhow, I'm invested now. I invest and advise in a lot of startups, and I've just founded OpenCV.ai to kind of make a product partnering and consulting company. Okay, so I'm just going to go through the background of OpenCV. I think probably you're all aware of what OpenCV is, I guess, or at least the ones working in vision, or you went over it. So it's a computer vision library I started. It's 20 years old. It's free for research. We just switched to the Apache 2.0 license. Someone's mic is on.
Please mute your microphones if you're not talking.
So Apache 2, there are open source licenses that allow you to do more things. We used to be BSD. I wanted the library when I made it to be free for research or for commercial use. Apache 2 is a little bit better because it gives you some patent protections, but it's free and open still. And it has all kinds of interfaces. Python, Java, and JavaScript are mature. Its base code is C++. It's a huge library. It has greater than 1 million lines of code, 70 plus modules, 2,500 algorithms. It's downloaded, but with Python, we think it's between 1 and 2 million downloads a week. So it's quite a popular library all over the world. We have a lot of contributors, and every year we run this summer of code where we get more student interns and they contribute. So the origins of OpenCV, in case you get your job, is I was in investment, whatever, as a quant in a financial trading options derivative trading department. I hated it. So this was after my PhD. I got back into research by joining Intel Research, and they wanted me to write papers and things to put Intel on the research map before their general need was, at that time, the processors had got fast enough to do Word and spreadsheets, and there was no real other use. Remember, the internet, that thing hadn't happened yet. So that was one of my jobs. But I looked around and I visited labs all over the world, and I just saw in computer vision and robotics a little bit. and everybody was reinventing the wheel. It was kind of chaos because you could never re-implement. It was very difficult to take a academic paper and implement it, because their code was spaghetti. It was full of bugs. When you re-implemented it was full of your own bugs, and like it's very difficult to believe if someone had repeated something or beaten it. You never knew. And so I decided to give a common infrastructure. Also, as happens today, even more, coding practices are horrific. So we have like state-of-the-art coding practices. If you just learn these coding practices, you'll probably get a job at Google, because those are the coding practices we use. And I also wanted to make the field faster to iterate, because my idea was to accelerate computer vision. And that's what motivated me to start this in Intel. I had to negotiate with them that this would be open source and whatever. And it all sort of worked in the years. And then after I left Intel, I would keep this thing going and keep the team going until till this very day. That's 20 years. So that's perseverance. Can pay off if you want to try that. Okay, so this is OpenCV at a glance. It covers computer vision very widely, from image processing, transformations, and I'll go into this, fitting, optical flow, segmentation, calibration, features, visual SLAM. That's where robot wanders around and makes a map and can navigate in it. So that's simultaneous localization and mapping. Where we have a 3D module, and this is being highly worked on right now. So we're going to have a complete 3D point cloud matching, octree, if any of you know all this stuff. And then, of course, we have computational photography, but the big thing these days is deep learning. So we have like comprehensive deep learning support. We don't learn the stuff. You can do it in PyTorch or TensorFlow or Caffe or whatever. But we can extract those models and run them efficiently across any architecture. It doesn't have to be a graphics card. It can be Movidius chips, run things at much lower power, and there's a lot of other things coming. So this is an overview of the history, 20 years of it, of OpenCV. Like I started it, I got the idea at Intel. OpenCV, it was CV Live at the time. Started as my disk. I cobbled resources together at Intel and started a team. The first public release was at this computer vision and pattern recognition conference, which if you go into computer vision, that'll be your big conference for the US. And so we released it there first, and it did quite well. Then 2005, I got into the DARPA Grand Challenge. I told you, like, we won the race that kind of kicked off the autonomous driving industry. We had our first official release. It was in beta before in 2006. And then, it went on and on. We improved the coding style. We moved from C to C++. We moved to GitHub. All these things you were born with, but they were innovations at the time. And we added 4 years ago. We started adding DeepNet support. We were actually the first ones, because I'm personal friends with Jan LeCun, who sort of invented the deep nets, and I added it years ago. I think in 2005, but no one used it, and it was very clunky and didn't converge at that time. So it finally died of bit rot. Don't I wish I had stuck with it more? But this is leading up to today. I decided starting about 2 years ago to really start revamping OpenCV, and so I've been growing the team, and like I said, which I'll get on, I've started this OpenCV.ai, which is doing contracting and product partnering, and it also contributes money back to OpenCV. So where we are right now, we're in our 20th year anniversary, and we're hoping to hit the release 5.0 at the end of the year, which it'll be C++ 14 compliant or required. I think we're going to drop Python 2. Well, I'm arguing just to drop it, go on to Python 3. We moved to Apache 2. There'll be a lot of other stuff, but particularly there'll be 3D and I've put a lot of other stuff, calibration, this is all robot relevant, color calibration and balancing, and I'll show some of these things. We also have courseware, if you want to. We have very high quality courses by an excellent instructor, and you can go through deep learning and whatever. First the use of it, and then into the details and computer vision on OpenCV. Okay, the DNN library, I said this is, deep learning has taken over everything. This is deep neural networks. It means multi-layers of neural networks. I don't know how familiar you are, but probably your whole lives will be involved in this thing. It's a method of learning stage-wise from gradients, and there's a lot of tricks. They called it convolutional neural networks. That was Jean LeCun's original name. And that's because there's tricks for keeping the parameters from blowing up, where you only look at little subsets, but you replicate them everywhere in the image. And there's a few learning tricks that really made this work, along with this massive compute that you guys didn't grow up with, but trust me, it wasn't always there. And also the massive data sets that you can now get. Before, if you wanted 1 million images, just good luck. You wouldn't be able to get them. But now there's databases, and cell phones have made, image collection and video ubiquitous, as you see on all the social media. Okay, so recent additions, like, and I don't know how much this, I threw these slides in. So, how much you guys are whatever cognizant of all this stuff, but we're recently, we got in contact with ARM, and we're the ARM processors, and we already have an optimized ARM module, and this little company called Huawei that's now under attack. But they donated a giant server to us for running all the ARM. Every time we build something, we have to run it and test it. So they gave us a giant, very expensive server to run to test things on. Whenever anything builds that's going to be checked into OpenCV, it has to pass all these tests. So one of these things is on ARM. We're also doing this for RISC-V. RISC-V is this reduced instruction set computer, so you can make very low power devices, and this is all like the movement of vision to the edge, like you were sort of born in the cloud era. Right now there is a movement of computing, what they call at the edge, on your device. Your phone is one example, but there'll be cheap little devices that have intelligence in them. So we're supporting that, and this is part of my job. It's like to keep up with the technology that never stops. If you let it get old, then it just goes out of use. And like I said, we have full support for most of the important things in deep nets, and you can learn on whatever tools you want, but you can run, if you wanted to run on RISC-V, you can train that on PyTorch or whatever, and then use our tools. Translate our model. We have tools into this DNN framework, and it'll run anywhere. Okay, we also run the Summer of Code, so you might all look out for this when you're in college and grad school, but Google runs the Summer of Code, so they pay you to be an intern over the summer. You work at home, which is like what you're doing with COVID. and we've been running this for years. So, we get a whole bunch of applicants. We have ideas. We bid against Google to see how many slots they'll pay us for. And then Google actually pays you to code at home, but it's mentored by someone who's more senior in OpenCV. I mentored the color calibration, that Macbeth chart. I don't know if I have this mouse comes through, but this Macbeth chart is something I worked with a guy in India, and then someone in Huawei is actually right now I'm working with him to do the color calibration transforms, and so they'll be donating that. And but there's these feature detectors, they're called SIFT, and we're speeding up things, and we're adding Julia bindings, the language to it, and JavaScript. We're getting that mature and tracking, and all kinds of demos. Down here, this large scale fusion, so you get a depth map, and as you go over it, you actually average onto surfaces, and you get this smooth, nice depth map. We now have state-of-the-art text and image detection. So all this stuff, if you just get the module, it will run on your embedded robot. You just have to figure out the right thing to call, and you're there. So OpenCV 5.0, it's coming out at the end of the year, and I've gone over a bunch of this stuff, but there's some of the chief things are, I already said it's C++ 14. It will have a much improved Python API, so it'll be more Pythonic. Not that maybe you're into it. Once you get more mature at programming Python, there's a style and whatever it should work with, and we're aiming towards getting more compliant with that style. But one of the main things is this 3D model module, and we've already added a state-of-the-art ransack. If you don't know what this is, it's when you're trying to get rid of noise in something you're trying to estimate. If you have you just sort of randomly sort the tries, and you see which ones are, so you take a random subset and you solve something. It could be calibration, it could be a location. And you do this, maybe 100 times, and you see which ones there's a consensus. So it's random sample and consensus algorithm. And so, we've moved to the state-of-the-art algorithm that's way faster than the one that currently exists, and it works better. So, there are mathematical experts who do this well, and they're paid well for it. But they donated it to us, and SLAM again is this mapping. So a robot moving around, it can form a map and then navigate within the map, and then various other things. God. The problem is there's something interfering with my arrow keys, so it's a little bit random bouncing around. But like I said, more ARM support. We're going to add audio support. So these are all things that are coming. This deep DNN is deep neural network improvements. We also got Tencent. If you know the company, they have WeChat is their communication platform, but they have like state-of-the-art barcode reading. So they're now in the process of donating that barcode reader to OpenCV. So, we'll give the world very reliable QR codes, these two-dimensional barcodes. And in China, they don't use cash anymore. They just use QR codes. So that same functionality will be in OpenCV probably by the end of the year. Well, I don't know when it'll actually get merged in. We're doing little legal work. So, I said I was revamping the team, and so now development is around the world. There are some of us in the Bay Area and also some in San Diego, but I have 2 teams in Russia. One is paid by Intel. They work for Intel, but I pay my own Russian team. It's 3 people right now. I'm trying to get that up to 5. And then we have extensive contacts in China, in Shenzhen. So there's a university team there, and we're also working with China Software Development Network. And as I said, like Tencent is now contributing this barcode reader code. And then in the community, so you can just sit outside, as many people do, and contribute something. It's a good resume item if when you're graduating from college, to have contributed to open source. So we have a method of contributing. The coding has to be to our standards, but even going through that process will teach you a lot. But we get from 2 to 5 contributions per day. This is why I pay someone full time to try to keep up with this, the gate master. So you can't contribute code unless you get it through all the automatic tests and then this gatekeeper to make sure the style and everything is up to the level. Otherwise, the library would just become a mess. So I have to have these people. I think I went through this. We get 1 to 2 million downloads a week. Most of that's coming through Python now, but there's a lot on other platforms. Surprisingly, Windows is still the highest platform. We're on GitHub, if you're familiar with that. It's a software repository where you can do collaborative coding, and I've gone through a bunch of this. these are some of the things. See, I've been revamping the organization. That means getting in money. So far, I got in $250,000, right? This year donated, and I'm trying to get that up to $1 million a year. It might sound like some money to some of you, but it goes fast, paying for developers and lawyers and all the other stuff we're doing. So we have companies that are in this gold sponsorship program. ARM may be joining soon, and a few others, and they donate money. We also have these hardware partners, so we're going to open this hardware store. And some of these people, did I put it here? Yeah, they're development partners. So these two companies are actually donating engineering time, and partly a lot of the ARM optimization is coming from this OpenCV AI lab, where they have maybe 4 or 5 engineers just working on ARM optimization for OpenCV. So they contribute money, and this is how this library stays vibrant and working. These are, we have a board. I formed a foundation and org. So these are all, lots of lawyer work, and we have people around the world working on this. So U.S., Russia, and China, and others, because we also that board sets our like business objectives. This board is the technical advisory board, so it's even wider. It's around the world, but we have technical discussions about what we want to do and how it should be implemented, and if there's any legal problems, and on and on and on. So roadmap. I've covered a bunch of this stuff. I'm aiming towards more support in the medical and robotics. See, that's what I do as the kind of chief scientist board member. I go, we should be in this area. So I really want to enable robotics, because the rollout of robotics right now is pathetic. There's not a lot of smart robots. And so I'm trying to make it easier for people to get together, not reinvent the wheel, and just focus on, their application without doing a lot of like needing a whole bunch of team and whatever, and a whole bunch of money just to get up to a running state, which is like vision was, 20 years ago. Everybody's reinventing the same thing, and then they're solving. And so I'm trying to, get it to have solid building blocks that people start from, and then concentrate on their areas. This is the ecosystem. So we have an org, which is nonprofit. I don't know if people know what a nonprofit is. It's simply a company where there are no owners. We can make plenty of profit if we want. We aren't charged tax, and no one owns the company. So it doesn't have stock. It just has memberships, and there's a whole bunch of IRS rules you have to follow, but it's meant for society benefit. So it follows all that stuff. It has education. We're doing membership and courses and whatever. And then I formed a for-profit that's sort of the, doing, because people ask me, can we implement something? So I have contracting services now, where we'll be opening early next year this AI marketplace for all kinds of these algorithms. We're starting this newsletter, and we have this product partnering in several areas. We're hoping to get this on to a lot of trucks soon, but we'll see. Yeah, this is just saying some more of the same thing, and the images have shifted somewhat. But what we do is we can take a problem, you could pay us off and we'll make your robot for you. But companies pay us in various areas to either solve problems or do their whole product. And we actually partner on products. So we're what we call white labeling. We have this camera, smart camera, that's going into production, and we're going to sell that. Again, I'm not doing things anymore solely for profit. I like money, but I've already can live the rest of my life. I'm done. So I'm trying to get things moving. And so one of the problems is like the smart camera and its support, I feel, are too expensive. So by getting the volume up, we're going to get this smart camera that will aid robots and other things, the price down. If you don't get volume, your price stays very high. So I'm trying to spread this out among a lot of areas, and then we'll have, you can buy this camera. You can actually buy it. So they're Black Friday. You guys should order it. So I'll get on to that. But I mentioned this courseware. We do paid courses, so to keep people serious. But our and to do that, we do an excellent job. This is not like me blabbing. It's a guy who's really talented in teaching, and a lot of software support behind it. So these are the first 3 courses, and that go from using, basically getting up and running, how to use it, and then details in deep learning. Okay, this I had mentioned the smart camera, so here it is, and it's actually there'll be a Black Friday sale. It was the biggest Kickstarter ever. So a couple months ago, we ran a Kickstarter, and it sold 1.3 million. Biggest Kickstarter for a smart camera. And so we sold 6,000 units. Since then, we've sold about 10,000 more, and we might be getting higher orders. This is some of what we do. We partner with people who are expert in designing this, and they partner with experts in manufacturing, and we're the software and sort of marketing for this. But I mean, in the end, it delivers to users, and to me, I want these things. This camera, one is a mono camera, and the other is a depth camera with the color image. And then it has all these models that run on that camera, and it's very efficient, so it doesn't use a lot of energy. Okay, so a tour. Well, I can stop at these blue points if people have questions. That might have been too long and too boring, but I don't have a clock. Are there any questions here?
Yeah, I have one. So basically, in the car automation industry, I think I'm aware that like OpenCV is being used quite a bit. But I also noticed that a lot of the sophistication of autonomous driving used to be relied on hardware, but now it's slowly moving towards cameras and vision software like OpenCV. So do you have any insight on why that might be, and also where do you see OpenCV being used in the future?
So I'm going to go through some car applications, but there's this, what happened in vision is when I started way back, when you were all embryos, nothing was working. It was a pathetic field. I actually felt guilty at one point that I was attracting people to work in it. And I go, these people will never have jobs because it just doesn't work. And like the gig is up eventually. But of course, the opposite happened. Everybody, like no one has suffered a recession who's worked in vision. But what's happened is these deep neural networks have kind of taken over many parts of vision. It's actually, you call it classical vision. It's actually used a lot in hybrid. So the pre-processing, and even now some of they're now even putting vision operators internal to the nets. But what's happened with all this? So we've had you have stereo vision or some other depth thing. There's LiDAR it's kind of a time of flight. It sends out a laser beam and looks for a return. And there are other kinds of depth sensing where you put out a pattern and you do stereo triangulation. So that's, you're just doing a geometry triangulation problem in stereo vision. But what's happened is AI is not only helping those things, but it's also competing with it. And so that, people are now doing depth from a single image. And you can do this yourself. Cover your eyes. You kind of know how far things are. You might have a little bit problem playing basketball, but I bet you'll find one-eyed basketball players and they can't see depth. They're only inferring it, right? So, in the same way that's happening. Now, there's Elon Musk. He doesn't like LiDAR and these other techniques, I think, because he's a bit crazy, but they were too expensive to put on his car. So he just takes the position, like anything else, all you need is a camera, everything else is BS. But it's not really true, because the cost of these depth sensing things, LiDAR, is coming down. Like it's already in the new iPhones. I think the iPhone 12 Pro And you know, it's amazing, like amazingly good images. So but you know, they themselves, the LiDAR itself, is also using deep learning and other things, but also classical calibration. So I don't know who wins this game, because there's nothing intrinsically expensive about LiDAR. So the thing is, cameras are developed for a long time. Now, you guys probably didn't live through this evolution. There was television that used to be big tubes. Maybe you're all born and you don't even remember television tubes, but it used to be like, and then they came up with flat panels. Like, well, like this, having a giant vacuum tube that can literally explode in your living room. Why did they, it took it like 20 years for flat panels to replace them. And the reason is, you know, there was so much tech, and they could build these, you know, monitors so efficiently that it took like 20 years for flat panel displays to catch up and finally be cheaper. It's kind of the same thing in the oil industry. People say, you know, fossil fuels, they just come from the ground, free energy, but it's not really. That was how it was in the early days, but there's so much tech that we're able to do it so efficiently. And, you know, that's why solar panels and wind struggle against fossil fuel, but they're starting to win, right? But it took, you know, decades. So I don't know, like cameras are so advanced now, and they're getting so small. And I've seen really cool things that maybe some advanced people are doing with cell phone cameras, whether they come out or not in startups, but, you know, making a cell phone camera as good as a single reflex camera by channeling the light, bending it around, and you know, like so I don't know. The long story short, AI competes with this, and yet hardware costs are also coming down, and LiDAR, I don't know who wins in the end. You know, but we're going to support both, and either the deep net also infers depth, and then we'll have ways of dealing with depth.
Come quickly, Anit. It's only last few minutes. You need to stop.
Okay. Microphone. But okay, I'm going to go on to this tour. You already saw this thing. Yeah, and maybe I should skip through. Well, I'll go through this pretty fast, these areas. Here's where I showed code, because I was told a number of you at least code. So, you know, you can do everything in Python, and you can kind of slap together things really fast. If you learn C++, you can get it more efficiently, but in the end, these things are running efficient C++ under the hood. So, you know, this is image processing, and I just show some simple code for doing what's called morphology. And it's a way of segmenting and cleaning up images after you recognize things. But image processing covers many other kinds of things: thresholding, resizing, you know, transforms themselves. So there's a lot of geometric things you can do with images. I show down in these images, you know, those four corners are now aligned. This is called homography. And, you know, so that homography maps planes to planes. And that's what's happening in a lot of computer vision on your camera. Yet the imager is a plane, and somewhere out in the world, you have a planar object, or like some little hole in the lens can be considered another planar thing. And so using this math, you can transform, you know, planes to different coordinate systems. And that's what's kind of being shown here. And OpenCV just makes this a few lines, like, you know, this is getting a perspective transform and warping it. So once you know those points and you're warping them to other points, you're done. And this is like the inside of calibration algorithms, like how they're like, I'll go on to calibration when I get there. But here, fitting things, and this is kind of simple stuff that might be useful in simple robots. And so it's shape fitting, template matching, normalized cross correlation. Here you can analyze shapes. So this is used a lot in factory inspection, you know, like putting on the labels on your shampoo. Those are all inspected by cameras, and they're kind of just doing this template matching. The thing should be within a certain area, and they're searching for the letters, and all this is happening at 500 frames a second, right? So every object you touch by now, like your clothing and your Coke can or whatever has been inspected by computer vision. So this is just one of the big growing areas of it. And this is one, like I'm showing, like that this fitting is some of the features that are used to analyze, what you get and how to make sense out of defects, detect them and flag them. Optical flow is like super big for robotics. It's the basis of in a way, it's the basis of calibration. It's the basis of SLAM, this robot's learning a map and moving around. And it's basically tracking points, point objects. Now, again, a lot of this is the points are now detected by deep learning. I don't think I put it in that list, but there's a lot of flow algorithms. My friend in doing agricultural tech I'll show a little film strip. He's only doing optical flow. And basically, because there's a delay in the film buffer, he's looking for features. These are good features to track. To Mosey, he was at Stanford, now, and it's looking for that feature, and it's tracking it backwards and forwards in time. Where it goes and starting there and seeing if it comes back. Those are reliable features. And once you have reliable features, when you look into the map, there's a lot of structure you can determine in the world. So optical flow subserves all this stuff. Segmentation is kind of what it sounds like. You're breaking out what the pixel. If it's a person, you're cutting them out from the scene. There's different levels of quality of this. Like one is like you're kind of there, and one is on the movie level where they're doing this kind of segmentation, and each hair has to be both. But there's lots of simpler algorithms that work for different cases. Super pixels can be used, grab cut algorithm. These are all classical algorithms that often work well. So, it helps to sort of know the whole toolbox. That's how you become an expert. You just get familiar with what might solve a problem. These days, a lot of people just come in and learn deep learning, but they really have no understanding. It really, like, some of the things have gotten down to what you might say is a high school level, where someone's running a script, but if what you want to do is, as you go through college, is get a really deep understanding. Same with just programming. You want to learn about computer architecture, and then you can really make things happen, right? Not just learning a surface level. But I talked about calibration, so I show some calibration. Again, it's planes to planes. So homography, mapping of planes to planes, is central to the internals of these algorithms. But here in the external, you're just finding a bunch of points on some calibration object, and then you solve for, the cameras have all kinds of problems with it. The pixels might not be square. They mostly aren't, by the way. And so, how do you stretch that in one dimension or the others? The pixels might actually be skewed. Now, manufacturing is getting better, but that was a big problem. They might not be lined up in straight lines. So this mathematically corrects all that stuff. But mostly now, because the manufacturing has gotten better, it's correcting problems in lenses. Lenses aren't perfect. They're bending light, and you get all kinds of edge effects, ballooning effects, but you can correct those out mathematically. And that's why you're looking at planes and how they're distorted, but it should not be a distorted plane. And you basically set up a system of equation and solve for the parameters that will map the planes to being flat. Meanwhile, you learn a lot about where those planes are in space and other things about your camera, where the center of projection is. Lenses have a center. It is never in the center of the image. With calibration, it mathematically moves it there. It's never in the center because the manufacturing doesn't have that kind of tolerance. The cheap lenses are glue, and glue never settles. And also the lens will settle at an angle. I'm being extreme if you see the video, but that distorts things, and this undistorts them. So there's an undistortion of learning how those things are warped and dewarping them, and then registering this, and then registering cameras to the patterns in the world, and also cameras seeing the same patterns can be registered geometrically together. And that's how you make a multi-camera robot. And I'm right now in the process of building a toolkit that will make that easy. Bottom left, I show color calibration, and this is important. If you see the Mars rover image and you get into the raw images, like every other picture, it's looking down on its color calibration to keep the colors and everything balanced. I'll show you later if I ever have time. I'm probably running way too late. Okay, this is SLAM, so I'm just gonna skip through because I'm gonna go way too late. So this is a camera moving in space, right? But they put it together frame to frame, and then there's something called bundle adjustment using everything. Oops, I don't know why. Ugh, skip the image, but this thing. Let me try to get this started again. So you know, this is something, a camera moving through a corridor, and there's something called loop closure. I don't know why this isn't playing. Okay, you know, once it sees where it was before, you can then rectify everything or make it like into, if it should be rectangular, you can. Yeah, so they call it loop closure. This is walking down a hallway in a building or a street. And so this is SLAM, and you can see like the features it's detecting, and it's putting together this map. This is a fundamental of robots. Let me try to turn off the sound in case that's there. In any of the case, so there's loop closure, and you see the whole system then becomes solved and loop close. So this is SLAM, simultaneous visual, that's the V, simultaneous localization and mapping. So you're forming a map and then maneuvering it. This is what you do when, you know, you walk into the new mall or something. You figure out where you are. Okay, stereo. I'm just showing the simplest stereo techniques are literally like 3 lines of code. But it gets more complicated now, but deep nets are doing a better job. Here's the deep learning, a full example. So a lot of this is just setup code, and the core of it, you know, really starts with this DNN, you know, call. They set up classes, and then they read through images, and it's pulling in a model, and it's just running, and it's labeling, like, you know, there's a dog. And so it's very simple to do, and you know, make use of it. This is something, you know, for coding where you can take deep nets, they'll run them raw if they can, but we also can optimize them. This is just 2 different paths. Like you run it through this model optimizer, and it'll run more efficiently. It's stripping out a bunch of things. It's computational photography. It's a huge field, but it can be really fun. So, you know, there's Poisson blending above. So, you know, we cut in 3 images together, but it blends them, and, you know, it makes it all look natural. Below is something called tilt shift. This is what would happen if you're actually tilting the imaging, you know, array, where your imaging chip in the camera. And so one part's in focus, the near and far is out of focus, right? And it makes it look like it's a toy miniature. This is a picture of the real arch, but it makes it look like a toy. So there's all kinds of fun stuff you can do in computational photography. That was the tour. Now I'm going to go through non-robotic uses. Does someone have the time? Because I'm lost in time. I can't see it on my screen and my phone's dead.
Yeah, so Gary, we are...
anyone want to yell out the time?
Yeah, we are 4:52. Yeah, so I think so let's spend a few more minutes. I'm sure students...
In either case,
questions. Yeah.
OpenCV for non-robotic uses, there is zillions. A lot of this is coming from this company, this contracting company I set up. These are various snippets of contracts that either we've worked on or the people we directly hired had just worked on, because we kind of work, again, partnering with 2 other contracting companies. We now are trying to take over their workflow, but they still have their own workflow, and they've done this stuff in the past. So people stuff is, this is visitor counting. Oh no, they did too much of this stuff in these slides. I wanted to kill this stuff, but so this is tracking people in a space and counting them. I hope there's not too much of this stuff. People detection, again, so this was a project done on field programmable logic arrays. where you can simulate logic, so you can simulate a CPU, but what happens is it runs very energy efficient. So, you can have a little battery powered camera that'll run for a month up there, doing pretty sophisticated things. Okay, it showed that the model, we were able to shrink the model very small. This is for advertisement, telling whether people are looking at something or not. Whatever. Been in conference where they do eye tracking, and then they put up images and embarrass you by what you're actually looking at. And sometimes it's subconscious, so your eyes go there and you see it go on the chart, even though you did look there. But we're doing a lot of stuff for, well, potentially got this contract in sports and training and exercise, like a magic exercise mirror that will look at you and count what you're doing. This is for, sports automated production, counting, tracking where the ball is and whatever. I don't know if on the net people saw this video. It was pretty funny where one of these algorithms, maybe it was ours, it got stuck on there was a bald headed ref in front on the front sidelines, and it thought that he was the ball. So for the whole game, it watched his bald head. But so it goes. Pose tracking, I'll show some of this stuff. Face recognition, this is just stuff we worked in. 3D data understanding, I talked about some of the stuff. This could be from a LiDAR, again, like not from a camera, but they're getting very good. So you combine it with a camera and you can like segment parts of it. Augmented reality, tracking a hand. I'm just gonna, we've done a bunch of work in medical, so 3D tomography, like trying to segment tumors or other structures. Did something for Nestle on skin classification and zits and all this stuff. Yeah, they did find, it was kind of interesting, because they had this power now, they did find that different races respond for these treatments like acne, they respond in different ways. So they never knew this before. So, sometimes you need more treatment or less. So it can improve outcomes for people. Some of the stuff we're doing in medicine is this blood flow analysis. So you can do this image amplification by carefully stabilizing on a surface and just averaging and amplifying that signal, stripping out other things. You can actually, with a camera, regular camera, you can see the blood flow in your skin. And you'll see it in a movie, you'll see it pulsing, right? And this is non-contact vital signs, so reading temperature and other things. Breath rate and other things. This is stuff we've done for COVID. I talked already about this edge-based, running stuff on edge, so vehicle detection, quantizing these deep net architectures. They have millions of parameters, but we can cut them down by lots of tricks. Other solutions. I'm just gonna keep going. Fashion, ag tech, we're doing a lot in. Reading text, again, these are models. This is segmentation like is happening behind me in Zoom. This is stuff from my previous company we did in the film industry, and we were tracking people who were segmenting hair. We worked with Will.i.am and in some of his videos. Now, this company unfortunately got sold to Matterport. Well, fortunately, unfortunately, it's a whole thing. If you get into startups one day, we were in a power squeeze by our VC. He forced the sale because it's complicated. They have different funds. VCs don't actually have funds. They call on people who promise to invest when they say, but these funds run for 7 years or 5 years. And so they ramp up, they run, and then they sell it out. We were towards the end of this fund, so he had to decide, is he going to roll us through in the next fund, or did he just want to just sell them and then he's off his books? He went that way. So he kind of orchestrated by power moves to sell our company. And now it's part of Matterport, which is doing indoor 3D scans. But this is some of the stuff we did, and tracking very precisely. So, you can see this thing looks like a video, but these objects aren't most of the objects aren't real. Let's see if I skip something though. So this is the pose tracking happening in a video. And again, these are deep models and we've just optimized them. And so it's getting pretty good. And now this might show up depending on funding and contracts in a exercise mirror that tracks how you do in a sports app. But here's some of the stuff we did in the film industry. This run, the SIGGRAPH is the top graphics conference where all the movie special effects people go. And this was a car, and you see it's being overlaid and turned into other kinds of cars. Here is like, so in real time, we're able to do this, but it's graphically overlaid. That's just that same car, but this is being overlaid in real time with graphics. And so they formed a whole movie out of this. And again, we did this in front of a crowd, and like it, yeah, they're actually seeing the raw car, but in the screen above, they're seeing what it looks like. And they're seeing themselves reflected in the car because it has cameras that are looking out, and it inverts the reflection. So that's one of the things we did. Are there any questions on that area? Tell me if I've totally overloaded you or put you to sleep, because again, I don't know what time it is. Oh, I see it, 4:49. I don't know if we can run after. This is now getting into OpenCV on in robotics. This is stuff I did, and I'm just going to jump it ahead. This was truck unloading. So we were the first one. Well, I went out there. I wanted to do robotics with vision, and I saw that manufacturing has robots. They're dumb, but this kind of supply chain, remember, everything you've got to you somehow, and it gets to you in boxes. So I go, why don't we just move boxes with the robot? It hadn't actually been done anywhere. And so we did all this, and then we did Larry Page's surprise birthday party, and then Larry Page bought us. And you know, we all go on with our lives. But again, this is a company I thought Amazon should have bought. So this is the car industry, and you know, I was on this team, Stanley. I don't know why this jamming up here, but you know, this was the DARPA Grand Challenge where they did this. These are autonomous cars, no one's in them. The first time this happened, you know, now these things are passing you every day, but that was the CMU. This was Stanley. There's actually radio interference, so it kind of glitches. That glitch is radio interference. Cell phones or something. But you know, it went on. That it was driving this course through a desert. This is where we were overtaking Boss, and you know, this is the LiDAR that we use. It was more primitive than it was today, but also cameras. But this is the 3D of when they stopped it to let us pass, because everything was running on time, not your actual place, but we kept coming up on that, so they had to let us in. And this is Stanley going down a mountain road. Again, this is the first real success of autonomous driving and what really launched the whole industry that some of you might end up working in. And that car was a chaser car. All it could do was stop the car, pause it or stop it, you know, for safety. But you know, this went on, and we won. So you know, it was one of those moments I knew, well, you know, this is a changing event in history, like, you know, autonomous driving. And that Stanley now sits in the Air and Space Museum. If COVID ever ends and you go to Washington, DC, go on the second floor and turn left and go back, and you'll see Stanley. It's in the navigation room. Anyhow, Stanley's brain, I might get into a little bit of this, but you can see these were the LiDARs above, and then it had a camera. So this was all fed into a world map, and then they were synchronized into a bird's eye view map, and then that was run through a physics simulator where it would doing a model of the car with physics, drive for a little bit, and then go. So this is the lasers would tell us, hey, I think this area is flat. The vision system would extend that area by segmentation. And so you see it at the bottom here. The laser gave us this trapezoid. We extended, and this allowed Stanley to go faster than the lasers could see. And then on the right here, I think this is supposed to be a movie, but it's not connected right. All these green and brown paths, this is the physics simulator running out. It says red is bad, this gray is good, and like this blue area, you know, is unknown. So run a driving simulation and pick the best driving path. That was how it was done. Again, I'm sort of covering robotics. So this is vehicle overlay and tracking. I already showed one of these things, so I'm going to move on for time. This is, you know, like your Zoom segmentation, but this isn't Zoom. This is something we implemented and our licensing. You can buy this. So, you know, it's free form background segmentation. She's being segmented in the scene. Down below is, or was, if I can find my mouse again, you know, it's vehicle, it's what they call a panoptic segmentation. So every pixel is being labeled sky, road, tree, person, vehicle. And, you know, obviously that's important for driving. This is on a farm near you. This is near Santa Cruz, where my friend now works, working on agritech. He bought a farm. Like, he was my co-founder in industrial perception and then array. And with his money, he bought this farm, and he's doing this optical flow. So these tracks are the good features that have been tracked forward and backward each time in this frame buffered in time. If they're reliable, they track for a while. And he's forming this model on the right that I don't know why it's not moving. Maybe it's supposed to auto. So it formed, and that's kind of the road that it passed. And this is totally naive. So it's not yet being what they call bundle adjustment. That's why the ground plane is not perfect, but that can be made perfect by putting it in a further optimization. But this is pretty good for just tracking point to point. They eventually go away and you go on to the next point, but it's putting this together in 3D using some odometry and differentiable GPS. Here's a tracking thing that we have running in the library. It's state of the art, so you can see where this might be useful in robotics and others. I think it's just, this thing's so big with Zoom. Here's a vehicle tracking and panda tracking, and then I think human tracking. And yeah, so it's pretty robust, you know, to hook onto an object. Well, that's part of the film going on for other things, but this is vehicle tracking and counting. And okay, so any questions on all that? And I have a few extra minutes, and I can go into, you know, there's the green pill and the red pill and the matrix. This is the red pill. Do people want to stick around and see it, or have they already dropped off? I don't know.
I think, yeah. So Gary, we have about 30.
Yes, no, because I can end here. That was OpenCV, but I will try to go on a little bit. This
Why
is
don't we
more for fun, to sort of blow your mind.
So do we have any questions? So I think
I mentioned how Stanley mind worked, and your mind, the whole point of this is you can learn a lot about your mind by studying robot minds. Your mind doesn't see the world, neither does Stanley. There are cameras and there's GPS, there's LiDAR, but it's all formed into a world map. Here it is on the right, if you can see my mouse. And the world map really has only a couple of components. It has white is good, red is bad, gray is I don't know, and it has a gravitational tilt from the inertial measurement unit that's in the car, and it's in your phone and whatever. And that's all Stanley has. And with that, it figures out where to drive, and it was able to drive for 7 hours across a desert. But that's the entirety of its mind. Now, the newer cars for the DARPA Urban Challenge and the Waymo cars, they have to do a lot more than that. They need a model of behavior, of how they behave, their own behavior in physics, and the other cars they see, because now it's socially interacting. Note that we're social beings. We're socially interacting. So are you doing this? Yeah, you'll see it in your dreams. There are other people who appear in your dreams, and you're doing this. You are socially simulating them. Soon we'll get weirder. The first hint of weirdness is, I just say this, like, when you wake up, the dream has not ended. It's just connecting to a data source. Like, you are actually living in the dreams, but it's no longer just free floating. And again, this robot is not seeing this thing. It's transducing the car into an object. It's on a graphic map where it's doing physics simulation and trying to plan out simulating the social, behavior of the other cars. Oh, that one's going to turn left. Well, now I know how to maneuver around it. And so you need the behavior of other things if you're going to plan how to behave. And that's called a causal model. You're reasoning in the causality. Like, this is going to happen if I do this, and they're going to do this. I'm projecting ahead. And you do this all the time. You're gaming your teachers. What are they going to do? What are they going to ask? You're simulating them. And so this is another little aside on your brain. What programs a human? A lot of people think it's their thought, but of course it's not. It's their emotions. If you're really interested in computers and robots, you're going to get pretty good at it, because it's going to focus all your attention, and you'll end up spending your career there or wherever. But this happens on micro levels of what you like to eat. It's going to make you healthy or not, and on and on and on. And so your emotions are what's programming you. Your intellect is sort of like implementing that plan for you, right? But it comes from something else. And Stanley's emotions was not all that compute. The emotions were, it really wanted to follow these GPS waypoints in order. Now, it wasn't enough to just follow them, because if you see, it would crash. This is a cliff. If it put itself right in the middle of this GPS point, it would fall off. That's why it needed vision to correct it. GPS is not accurate to that level. Okay, so now I'm getting to the brain. If you have a cat or a dog and you play Shakespeare to it all day long, as it's a puppy or a kitten, and it grows up, you don't expect it to learn Shakespeare, because its brain just doesn't have, the human wiring and whatever to understand it. If it understands it at all, it's some kind of dramatic meowing that like a cat would do. That's how it would explain it to another cat. And it's not really getting it, right? So I'm doing this with Stanley. Stanley has this very simple brain. It wants to go from point to point to point. And how would Stanley understand Shakespeare in its mind? All it has is gray, I don't know, red is dangerous, and white is good. And I want to go here. Well, Shakespeare is mostly about tragic heroes. So you could, in Stanley's mind, it could sort of understand Shakespeare to understand that the tragic hero might cut across this gray, taking great risk and probably eventually dying because of its foolishness of not going the long way around. So that's how Stanley's mind, with what it has, can understand the world. You understand now that the world it's not seeing the world. It's seeing a weird model of the world. It's causal. Its causal model is good enough to keep it on the road. But if we want to extend this causal model to think about other things, like maybe you guys have had physics and the particle is a wave, down small, things behave as a particle or a wave. And you go, no, it's not. It's just a breakdown of your causal model. You don't have the metaphors with which to reason in reality about that. And math helps extend it, but math itself gets weird. So in Stanley's mind, you can think, how would it use to explain Shakespeare? Well, it's the one who takes a risk by driving across the gray, right? It might hit the red, and it often does. So it's a tragic hero. So that's using Stanley's simplified mind to kind of understand our much more complex mind. Again, we're more complex. We're working more in 3D. We have much better simulation and whatever, but kind of the rounding error, we're not much more complex. We have a limited mind, has a causal model, and you're not really seeing the world. You're seeing your model of the world. And so that's the kind of point. There's not too many. We'll see how many slides. I want to show you that this is actually true a little later. But so your mind, or robot mind, it simulates the world in order to plan. That's a causal model. Causal things happen. If this happens, then that's causality. And so. And you need to simulate yourself because you're operating the world, and you need to simulate others when you're socially in the world. And so you actually have a social simulation of yourself, And that's what I believe is consciousness and what you're experiencing, not yourself, but your simulation of yourself. And this is why it's so hard, like, to change your moods. Like, you meditate to calm down. Why don't you just say calm down? Because you're not really connected with your body. You're connected with your simulation of your body, and you have to do this stuff indirectly. So again, the simulation is not a true representation. It's a causal representation. It means it can decide things that matter for itself to survive or get its job done. The same thing is in your computer. There's a trash can. I'll tell you, it's not a real trash can like on your computer. Not a real trash can. Do you believe it? It's actually, a physicist would say, aha, you're right. It's made up of quanta. It's a quantum. You go, no, actually the real world is much different than that. It's a von Neumann architecture, and this is just a causal expression. The one thing that's true is if you drag a file in there, it's gone. Well, after you say, okay, it's gone. And like, if I tell you a car on the road is not a car on the road, but if you stand in front of it, it's going to, put you in the trash can. It'll delete you. It's a causal model. What the real reality is, I kind of promise you this, is entirely different. As much different as your graphical interface on your computer is from what's really inside the computer. That's our relationship to the world. It's a causal model. Your graphical user interface is to be able to make use of your computer, to write files, to store them, to socially chat. And what's happening underneath the nature of reality is completely different. It's a computer. You can learn about it in college, So I'm probably getting ahead of myself, but humans are not so different. And things get strange. You're walking down the street, the houses are about the same size, and yet they're not. And lines are parallel, and yet you commonly see that parallel lines meet in the point. So these are things like the world is a little bit stranger than it seems. Your model is warped, and so parallel lines do naturally converge in a certain geometry that your mind uses. And you'll see your eyes. You'll notice
let's do a time check.
The angles that your eyes are looking are wide, but when you get far away, there's hardly any difference. That's why you can see, the difference between your fingers. But if you put someone's hand at 40 meters, you can't really see which finger is in front of which. It's because we have this natural logarithmic perception of the world. And your brain is actually structured this way so that it doesn't bother you that houses are actually the same size and different sizes at the same time, because they're sitting in the geometry of your brain where both those things are true at the same time. Here's some of this, they call it vergence, but it gives you a kind of logarithmic graph. And when you're in a 3D world, you get this log, very strange geometries, right? That's what you're really living in. That's your computational substrate. So this is, just supposed to be, kind of like a taking the red pill of what the reality is. This is just for fun, and you can take the blue pill and forget I ever said any of this stuff. But so we have a causal model, causally sufficient model of the world, and that's what we use to think with everything. Remember the cat and Shakespeare and whatever. And you can only think with things that your causal model has enough extension to. This has other implications. Are we ever really going to get a full understanding of reality? No way. No more than your cat is ever going to understand Shakespeare. We can push it pretty far. We can build a machine that can go further. Should I stop? You're waving.
I think, yeah.
I can't hear.
I think you're muted, Gary.
Maybe I turned off sound. Okay, sorry. Hello?
Yes, you're muted. Yeah, I think.
Sorry. God.
Yeah, so I think students are waiting to ask you a few questions after you conclude. So
yeah, sure. So let me just speed through this because I like blowing people's minds, and then this is drug-free blowing minds. One of the things I like to say, well, here's a question for students, like, look up at the ceiling and what is above that ceiling, or look down at the floor and what's below that floor. And well, you can see it in the picture I have right here. So what's right beyond what you can see is the surface of your brain. Right, that's, you know, right below this desk is brain matter or skull matter. That's the world we're living in, not in this external world. That's one of the points my you know, graphic artist friend was helping me make here. And again, well, this is the thing. So what's beyond the sky? It's the inside of your skull. That should be obvious. And if you go read Plato and all this stuff, you know, pay attention. Plato realized all this stuff way back then. Like, he's one of the great, you know, geniuses of all humanity. These, you know, ancient philosophers. Of course, he didn't have all the tools and understanding we have, but like they realized a lot of this stuff. This is Plato's cave. But again, I told you we simulate the world, and this is sort of a pictorial thing. We have the strange geometry, and this guy is in mine and I'm in his, and you know, this is what a robot must do at implicitly or explicitly. And you know, I was saying that you're actually simulating yourself, and I think it's in the social simulation of yourself that's consciousness and self-awareness. It's a byproduct. Not that we can ever understand it, but that's about as close as we can get. And maybe with that understanding, we can actually reproduce consciousness in a machine.
Okay, I
so
think, Gary, yeah, let's see if students have any questions at this point.
Sure, you can ask a question, because I'm almost sort of done. I just wanted to show you some things where to prove to you that I'm not just, you know, high. And here's simple view of the world, why the world's so much different than you think. Look, here's a triangle and a circle, but just different views of it, left and right, give you totally different realities, right, of your perception. So you start seeing this. And now here's a famous scene in Stanford. And now you see that little guy. It's the same, you know, that's the guy you see in the back, but you see him as the same size, but yet as smaller. That's exactly what I've been saying. Here's something, I don't know how this is coming out. Can you see there's two different pictures here? And
yes.
they're why many pixels are different, like hundreds and hundreds of pixels are different in these two scenes. Can anybody see that? This is called change brightness. I keep telling you, you're representing the world inside and not outside. And I'm going to spill the beans to move fast, is the shadow of the helicopter. The reason you're not seeing it is there's a gray frame in between. Now, if your movie is screwed up, you'll see this right away. The gray frame's screwing up your motion sense, and therefore your attention. The reason why this doesn't happen to you all the time is your attention will snap to that shadow going on, but the gray frame in between, which you can kind of see, is messing up your motion signals. And when you see a magician, that is all they're doing. They're playing on this attention factor that you're really living inside of your head, and they can do anything. And trust me, go search the web. It's called change blindness. Go search it. You'll see people doing this wide. You'll see people ducking down below a desk. A guy talks to someone, ducks below, and a female stands up, and people don't notice, right? And so this is a real phenomena. Here's other examples. Colors. If I told you colors don't exist out in the world, they aren't the property of the world. They're a categorical property of perception because you needed to find seeds in the forest or something. So these two colors, you know, green and yellow, they're actually green. And this is something, there's a famous Alioski's a Japanese guy, comes up with zillions of these things, but the yellow spiral, so they are exactly the same color. That yellow and that yellow are exactly the same color, no difference. But you're using context to see. It's called it's called color normalization. And you need this so that when you walk outside, your shirt doesn't look a completely different color. You're only getting the relative colors of things. And this is directly tricking your system. Again, here's your eye, and your eye is kind of designed weirdly. The light flows from, your receptors are turned backwards. It's as if you turn your thing, you're only looking in a reflection. So these cones and rods here are what's receiving the light, but it goes through all the machinery and blood vessels and everything to go there. It's as if this eye evolved and was terribly kind of done. There's the reality. Everybody has a blind spot, and the fovea is here. That's where you have your high resolution. And you'll notice at night, go look at a star, a dim star, it'll disappear when you look at it. In order to be able to see it, you don't see black and white in your fovea. That's outside. And you can do other things like stare ahead and move something away from you, a color thing, and you'll see that your color vision doesn't go very far outside of your fovea. It goes maybe 45 degrees. Again, this is just showing the direction of light. At the top is, oh God, the direction of light goes through all this tissue to get to where it goes. It's the octopus eye has that turned around the right way, but humans did it wrong. Again, another thing is the optical axis where the light goes straight. That isn't your fovea. Where the focus isn't where it's supposed to be. Why we evolved this way, I don't know. Some people think is you actually, when you turn your eye, you get a little bit of parallax, which is a little bit of sway, and that helps babies figure out what's an object or not. That's one theory. But you know, this is just strange designs. These are some illusions. Like if you see a blue square on the left, it's not really there. It's just bleeding out color. Again, you know, on the right and in this thing, you can see, you know, this is called neon color spreading. Yeah, showing that it goes away. The neon color spreading happens in 3D. So you should kind of see a 3D sphere if it works for you. Again, you know, our lighting and relative adaptation. Are these colors, are these two shades of gray? This is a famous illusion. No, they're the same color, obviously. If I asked, my computer, shoot. Okay, there they are. So two shades of gray. Again, things look different according to lighting. You're structured to learn the world a certain way, and you know, it can look very different if you just swap the lighting around. Again, here's a scene. You know, what is this that I have a picture of? It kind of look sort of weird the first time you see it. Like it's hard to know what it is because it's breaking the assumption that light comes from the top left. You see a lot of ancient artists, they bring light from the top left. That's where you like it. And you know, when you do that, it looks much simpler. Turning, this is motion. Again, your motion system does not rely on color or anything. It only relies on contrast. So when you blend the contrast, hopefully this is working for you. Wherever you stare, you'll see it fixed, but wherever you're not staring, it looks like it's moving. So because all you're getting is contrast and not the color out there. So these are called motion illusions. It happens in 3D. This one will only work if it's at the proper resolution for you. But for me, everything is spinning in 3D. And I'm just, okay, so here's another one. This is context. There are no red pixels in this image. It all comes from your assumptions. So you can, you know, these are a kind of color of gray, these strawberries. They're not red. But again, like I said, color isn't real. I'm almost done. So, you know, this causal model is what we live in and what you see. And it has all kinds of philosophical bounds for everything. It's why, you know, these two political parties can be so different in their reality because we don't see reality, we see our model. And if you put junk in your model, that's what you're going to see. So then that's why science, it's like tennis is not natural. You have to learn to hold the racket in this awkward way. You play for like years and then it becomes like, you know, you get in your muscle memory. Same way math and science must be studied for years to like get over it, these built-in assumptions, which were great for when we were creatures in the savannah, you know, beating up fellow tribes and whatever. Again, I already said some of this stuff. I don't believe there'll be final theories of the world because most of the world we will never comprehend, no more than the kitten comprehends Shakespeare. but we can push it pretty far, and we can build machines that are better in themselves. And kind of like we would do with if the cat asks us, what is Shakespeare? We would say, it's like a kitten that's too bold. The cat said, oh, I got it. And you go, no, you don't get it. But we can build machines that would understand further, but they themselves will be almost as limited as we are. And when we ask them, no, what really is consciousness? They go, oh, it's easy. And they go, no, tell us. And they go, it's kind of like you're seeing a causal model and of yourself. I don't get it really, but they can't explain it. You can't explain to something that doesn't have the circuitry to explain it. Whatever. I think these kinds of principles will help us design machines that can do all kinds of interesting stuff. I'm done.
Awesome. I think this was
yeah, that's the mind-blowing stage. So that's what you get.
Yeah. So why don't we give a few minutes to students to ask questions?
Sure.
You can unmute and ask questions now.
Yeah, if someone wants to unmute, I don't even know. Yeah, I'll keep this on the. Anyone?
I know. Yes. Oh wait, you can go first.
No, go ahead. Go ahead.
Okay, yeah, so I was just going to ask, earlier in the presentation, you mentioned something about medical diagnoses or medical operations being done with OpenCV and Vision.
Yeah.
Could you elaborate a little on that?
So Vision is operating more and more in the hospitals. And one of the things that I hope is coming out soon is a project I worked on with a company I worked for. It is a COVID kit. So I have these kits in the house where you stick something up your nose, you put it in a reagent, you drop it. It looks like a pregnancy kit. It's a little plastic cartridge, and a line appears. If that's a calibration line that just reacts to the reagent, which is something that dissolves things. But if another line appears, that's antigens that are binding with actual COVID particles. So it's a COVID test. The problem is people are flaky, as you might have, you'll realize as you get older. And so we want a camera to read that. And this is just a simple application. What we do is we have AI in the camera. It takes a picture and then it reads. And it also makes sure you wait for 15 minutes in case subtle responses are happening. And so you start the cell phone, it steps you through, and then you take a picture of this thing, and it will tell you within 15 minutes whether you have COVID or not. And then we have the picture to refer back to, but to make sure people aren't doing crazy things, I'm using a bunch of this geometry in OpenCV because if the AI says, hey, I read the test well, I go, well, then that means you must have seen it. And if you must have seen it, it must be about in this orientation. And that means I look at the geometry of the cartridge and I must find like the lettering and whatever within a certain bounds. And that's to keep people from making error. And then because I know where these things are, I've got that homography plane to plane. I can then indicate to the system, you should flatten out your camera to the left or the right. And so this helps people take it. But that's a simple thing to allow humans who are, pretty, you get very smart to very dumb out there, right? And it allows them to operate something at scale, I hope. And that's a product I helped do. But that same company has other things that they're trying to, let me see if I can find some, other things that they're trying to do. And, this is one of them. So one of the things they're doing is in childbirth, the woman could have a lot of blood loss. And it turns out they have 10 different levels of blood loss. And if you get too much, like the woman could actually get brain damage or die, but right now what happens is a surgeon, they're draining off the blood. This is all very gross, right? And there's other fluids. And then the surgeon's looking where the red level is. Yeah, that's too much, but there are rags and other things. So it's just an estimate. And that's what, the life is in the hand of this doctor. So we made an automatic tool that they have all these rags, they get red, but they're filled with all these other liquids. And this thing estimates the color, estimates the content of blood in the rags. The rest of the stuff is draining off into a tank, and it separates liquids that float from the red, again, by color. And we actually have they drop in a piece of plastic that is white, so we know how red it should be. So we can estimate how much blood is actually in that. And so we get a much finer estimation of the blood loss, which allows them to, you know, when they're giving birth or they have a cesarean or all these other things, they know exactly how much blood is lost. So it keeps, you know, they can do the exact protocol. They know what to do. They just don't know when to do it. And this, you know, has, you know, less women will get damaged or die or whatever. You know, I sometimes wonder, like, sometimes there's a postnatal depression or whatever. It might actually be like a brain damage that heals, but you know, that might happen less if this is done. So that's one product, and that product is selling and going on. Here's another product that I have the picture of. It's blood flow. And why would you want this? Well, let's say you're doing plastic surgery and you're cutting something. You don't want the blood. You want to make sure the patient under anesthesia or whatever you cut, they're still getting blood. If you come in with like a motorcycle or biking injury, you want to make sure that limb is still getting blood, or they should treat that first, right? The other thing is when you take any anesthetic, and this is weird, I've seen this imagery using this blood flow. You take a tranquilizer or whatever your anesthetic is, you see the blood doesn't pump as hard. Like your hand starts hollowing out of blood and whatever. So you want to make sure, like in the future, that your limbs and everything are getting proper blood flow. What do they do now? I don't know. By experience, it works on most people. You know, as you go into hours of surgery, this is all kind of stuff you don't know, but you'll learn as you have people who get older and go through this. A lot of times in heart surgery, the people might have years of recovering, like they can't sleep anymore. It's a form of brain damage. And if we had better control of the blood flow, that would happen less, right? So that's a product. And so this stuff is very useful for like real human health. And so they can watch limbs and whatever. It's just a camera. It's running in an iPhone. That's the product. And we're hoping like they'll start using our smart camera. But so that's one thing. And this is vital signs. So it turns out if you have COVID, your breathing rate changes. But if you have any sickness and whatever, your breathing rate changes. And, you know, so we can tell what your pulse is, your heart rate and your breathing rate, and you can tell a lot about a person. So if people are just passively, let's say, walking in an airport and someone's sick, you can pretty much tell this, right? So this would kind of be a passive thing that might select, you know, tell people that they're sick. Or in a hospital, you probably don't want someone spewing germs running around, and so, you know, in the future that might be a lot more controlled. So when you're sitting in the waiting room, someone who has the flu isn't walking right by you. So longer answer than I wanted. There's a lot of uses.
Let's have one final question for Mr. Bradski.
Yeah, so I know you mentioned earlier that I think you're talking about like a smart camera and how you wanted it to create a larger volume so it could be a more affordable product. And I was wondering, since OpenCV is used in so many applications, where can you see it if the price point of different hardware that can maybe use computer vision software becomes more affordable for a lot of communities? Where do you see the software being implemented in the future for maybe like a greater audience?
Well, yeah, so this camera we're already selling at $199 and $299, but it is like you know, way more than well probably like an iPhone worth of compute at least, or more in this. So it's like a full computer in this camera package. So you're getting a lot, and then the software. So where I see it in a lot of areas, for one, it could just be a home security or watch your pet kind of thing, but it allows a lot of applications. For instance, in the hospital, are the nurses washing their hands? with that body tracking or that pose estimation and depth, you can pretty reliably say, without even identifying the nurse, you can buzz, like, sometimes people just forget, and you can buzz and say, like, hey, you're walking up, but you forgot to wash your hands, right? There's another thing, like these cameras, if they're spread everywhere, I've seen this done, I'd like to do it. When a nurse comes in your room or a patient, they're touching things or they're leaning over things. There's this kind of thing, like in a 3D model, they spread a digital dust there, and you can actually see the areas that have come into contamination. So when someone comes in to clean, they'll know where to clean, right? And so like, again, this is kind of like the startups you might be able to form, using this kind of stuff, that anyone could take this in many directions. Robotics is a big one. Like right now, hand-eye coordination is very difficult. Only the most advanced companies do it, or people spend months just doing simple things. Well, I'd like to, or a company can work on that and get it simpler, right? I know a company that's simulating millions of objects in a physics simulator, and this robot is just learning to pick it up, where it won't tip over, where do you hold it that it's not rotating, and so it learns millions of objects, and it learns itself how to generalize, how to pick up anything. Well, then that could be a component in a system that then other people can use. Now, I'm an advisor there, so they got their first sales, and they're trying to get their first money and not run out and blow up and do all that stuff. But I believe they're in a pretty good position. And as they get more stable, I'm as their advisor pressing them, like, let's license this. Not, maybe it's a restricted license. You can't do it in industrial apps. They're doing pick and place. But I go, well, this is useful in agriculture and whatever. And like, if it becomes a cheap enough component, then other people don't have to go through that learning thing. Now, there may be other people who train models that approximate that for free, but I don't really care about the free part of open source. I just care that these techniques spread. So the cameras enable, then these models can run in the camera. For instance, if their algorithm was redacted to run in this camera, then you can get a ARM manufacturer, and that ARM just knows how to pick things up. Then what could you do with it as a company? Well, you can pick up, oranges, or you can, whatever it is, that applications you'll come up with, sort trash or something like that. And so, that's the kind of thing that it allows to spread. We're trying to get together a driving stack, so that thing, like, not so much for cars, because there are big companies of very good people who are doing this, but for carts and other things, and for outdoor applications, that you can have a little cart in your backyard that knows how to drive and get to places, can help you carry things, or could do weeding or whatever, just games. So that's the idea of trying to generalize this stuff, if that's answer to your question.
Yeah, it's great. Thank you so much.
Yeah.
Yeah, so I think we're a little
way past time.
Yeah, so I just want to thank you so much, Mr. Bradski, for coming in. I think it was a super cool presentation. Obviously, we've used your software in the past, so it was really awesome getting to hear from you about sort of how you created it, the whole process, and then where you think it can be applied now and in the future. So do you have any contact information you'd like to share with everyone who's still here?
So it's, I'm Gary Bradski at almost anywhere. So I'm Gary Bradski at gmail.com is the one I use for personal and other stuff. And it's, well, Google ignores the dots in the name, so it could be Gary.Bradski, but it's Gary Bradski without a dot, and at Gmail, or at opencv.org, or at opencv.ai. And like, if you've got something and I ignore you, then send it again, and I ignore you again, then send it again, because I'm not trying to blow you off. I get a lot of emails, and I miss a lot of stuff. I'm not trying to be rude. If I'm rude, it's because I just didn't see you, or I saw it and I was going to answer it, and then I forgot a phone call, and then you're gone, you're lost. Like so, you know, if you really want to contact, then contact again.
Yeah, so I think that wraps it up. Thank you to everyone who came in today. I know we had a pretty big audience, so I really appreciate everyone for coming in. Obviously, second thank you to Mr. Bradski. And yeah, reminder, we're having that alumni panel next Saturday. So if you're interested, the link is up in the chat. We'll also be sending out a whole bunch of reminders about that. So if you're interested in that, it'll be a very different topic, but hopefully it'll feel relevant to a lot of you. So yeah, thank you so much, Mr. Bradski.
Yes, thank you.